June 16, 1964. The Japanese port city of Niigata awakens to a 7.5 magnitude earthquake. But what happens next defies all expectations. Instead of crumbling, entire apartment buildings begin leaning at impossible angles, some tilting nearly 30 degrees. These concrete giants remain remarkably intact, their windows unbroken, as if frozen mid-fall. This surreal scene would become one of the most studied phenomena in earthquake engineering history. Engineers arriving in Niigata faced a puzzle. The buildings showed little structural damage, yet they stood at dramatic angles. The answer lay beneath their foundations. The loose, water-saturated sand that made Niigata's reclaimed land ideal for construction had turned against the city. During the quake, the ground had behaved like liquid, a phenomenon called soil liquefaction. Soil liquefaction occurs when seismic waves pass through water-saturated, loose sand. The vibrations cause water pressure to build between sand grains, reducing friction. At a critical point, the soil loses its strength entirely, behaving more like quicksand than solid ground. Buildings don't collapse so much as float into new positions, their foundations no longer anchored. Niigata presented ideal conditions for liquefaction. Built on reclaimed land near the Shinano River, its subsurface consisted of loose, young sand deposits saturated by groundwater. The long duration of shaking, nearly 2 minutes, allowed water pressure to build gradually. When the critical threshold was reached, the transformation was sudden and catastrophic. Remarkably, most tilted buildings in Niigata remain structurally sound. Their reinforced concrete frames flexed without fracturing. This demonstrated two critical facts: Japan's seismic building codes worked for shaking, but failed against liquefaction. The buildings were earthquake-resistant, just not foundation-resistant. Liquefaction doesn't affect all ground equally. As buildings began to sink unevenly, their weight caused further soil displacement. The process became self-reinforcing, one side sinking deeper than the other, creating the dramatic tilts. Some structures rotated on their foundations like ships listing in harbor. Survivors described surreal experiences. One resident recalled watching his apartment building slowly lean over as if in slow motion. Others spoke of the ground undulating like ocean waves. Furniture slid across rooms, yet glassware remained in cabinets, a testament to the gradual, rather than violent, nature of the tilting. Traditional shallow foundations proved disastrous in liquefiable soil. Spread footings and mats simply sank as the ground lost strength. Engineers realized buildings needed either deeper foundations reaching stable layers, or soil improvement to prevent liquefaction altogether. Niigata became the case study that proved this. In the quake's wake, engineers made startling discoveries. Some tilted buildings were jacked back upright and remain occupied today. Others became permanent monuments to the disaster. The most important legacy, however, was the complete overhaul of seismic design standards worldwide. Japanese engineer Kenji Ishihara pioneered liquefaction research after Niigata. His laboratory tests recreated the phenomenon, proving that cyclic loading causes poor water pressure buildup. The Ishihara diagrams he developed remain fundamental tools for predicting liquefaction risk today. Today, engineers use multiple techniques to assess liquefaction risk. Standard penetration tests measure soil density. Cone penetration tests analyze resistance. Shear wave velocity profiling maps subsurface stiffness. These methods help identify areas where the ground might turn to liquid during quakes. Where liquefaction risk exists, engineers now employ countermeasures. Vibrocompaction densifies loose sand. Stone columns provide drainage paths. Deep foundations bypass weak layers. In extreme cases, entire sites are avoided. Niigata's lessons transformed how we build on unstable ground. Post-Niigata, building codes worldwide incorporated liquefaction provisions. Japan's 1981 seismic code became the gold standard. The US followed with NEHRP recommendations. Today, international standards require liquefaction analysis for all major projects in seismic zones. Subsequent quakes confirmed Niigata's lessons. The 1989 Loma Prieta earthquake liquefied San Francisco's Marina District. Christchurch, New Zealand saw widespread liquefaction in 2011. Each event refined our understanding, but Niigata remains the defining case study. The tilted apartments of Niigata stand as permanent reminders of nature's power. But more importantly, they represent a turning point in engineering. What began as disaster became knowledge that has saved countless lives in subsequent earthquakes worldwide. Today's engineers build on Niigata's lessons. Advanced materials like shape memory alloys allow structures to heal after quakes. Base isolation systems decouple buildings from shaking ground. Real-time sensors monitor structural health. But the fundamental lesson remains: understand your ground before you build on it.